Hey everyone, it's Daniel. One of the most popular ACT math topics is how to work with a matrix. This has really started to show up more and more on the test over the last few years. My students are often stumped by these questions, especially since many of them don't see this topic in school at all, and those who do often still find it challenging. Multiplying a matrix could be complicated, but once you get the hang of it, it's less daunting than it seems. It just takes a little practice. So in this video, let's look at the different types of matrix questions you might see on the ACT. We'll start easier and we'll get harder as we go. If you find any part of this video helpful, please leave a comment, share, and subscribe. And be sure to hit the notification bell so that you could be updated whenever I post a new video. And you guys, the pictures for this video took so long to make, so if you find them helpful, hit that like button. This video took me a week. But seriously, I do appreciate your support. Okay, back to business. Let's get to how to work with a matrix. A matrix is just a clump of numbers, so to speak. They might appear in parentheses or in brackets, like this. A, B, C, D, 1, 2, 3, 4. So let's start with how to add two matrices. Question 1. Matrix 1, 2, 3, 4 plus another matrix 5, 6, 7, 8. This is less scary than it looks. All you're doing is taking any given term and adding it to its partner in the same spot, so to speak. So that 1 is in the top left. That means we're adding it to the other term that's in the top left, the 5. So in the top left it would be 1 plus 5. And now you're going to do the same thing for each spot. So the top right would be the 2 and the 6. They're both in the top right. And same for the bottom left, the 3 and the 7. And then in the bottom right, the 4 and the 8. And then you would just list those sums. So in each spot it would be 6, 8, 10, 12. And the same goes for subtracting. So to add or subtract terms in a matrix, combine the terms in each corresponding spot. Let's look at another. ABCD plus EFGH. All we're doing is adding terms in the corresponding spots. So in the top left, A plus E, the top right, B plus F, and so on, C plus G, and D plus H. You just add each term with its corresponding partner, so to speak. And the rule is the same for subtraction. Another variation you might see is a scalar matrix. Let's look at one. Question 2. 3, and then the matrix 1, 2, 3, 4. This means to take every term in the matrix and multiply it by a scale of 3. So all you're doing is taking the 3 on the outside and distributing it by multiplication to every term inside. So that would give us, for each spot, 3 times 1, 3 times 2, 3 times 3, and 3 times 4. So that would give you 3, 6, 9, and 12. So to solve a scalar matrix, multiply each term by the number on the outside. And let's just look at one more. A times B, C, D, E. Take the A and multiply it to each term. That would give you AB, AC, AD, and AE. Not so bad. Okay, now we're warmed up. Now let's get to multiplying with a matrix. Before we get to the nitty-gritty of how to multiply with a matrix, let's first look at the components of a matrix. A matrix is made up of rows and columns. So for example, given this matrix, ABCD, you can see that there are 2 rows, up and down, and 2 columns, side to side. And the world of math wants to use this notation for that. They're going to give you R by C. That's not a multiplication sign, by the way. That means rows by columns. So in this case, that would be 2 by 2. 2 rows by 2 columns. Let's look at a few others. In this matrix, we have 2 rows and 3 columns. That would be 2 by 3. And in the second one, we have 3 rows and 2 columns. That would be 3 by 2. Now here's why all of that is important. You can only multiply matrices if their product is defined. And in order to determine that, a matrix product is defined if the columns of the first match the rows of the second. Let's give that a visual just to make it a little more clear. Whenever you multiply a matrix, you always list the dimensions of one and then the dimensions of the other, and you list it rows by columns and rows by columns. And when you do, the columns of the first must match the rows of the second. So look at those 2 inner numbers in the box. Those 2 numbers have to match in order for a matrix to be defined. So let's look at a few examples. Can you multiply AB? You want to start by listing the dimensions of each. A has 2 rows and 2 columns, 2 by 2, and B also has 2 rows and 2 columns, 2 by 2. So a 2 by 2 and a 2 by 2. The two numbers on the inside match the columns of the first to the rows of the second. So that matrix is defined. You would be allowed to multiply them. Let's try another. Can you multiply AC? We have to list the dimensions of each. A is still 2 by 2, and matrix C now has 2 rows but 3 columns. We have a 2 by 2 and a 2 by 3. But the numbers in the middle still match, so we are allowed to multiply. That product is defined. And now let's see if we could multiply AD. A is still 2 by 2. Matrix D has 3 rows and 2 columns, 3 by 2. So now look at the two numbers in the middle, 2 columns and 3 rows. This is an undefined matrix. We would not be allowed to multiply. So, before you start, you always have to ask if the columns of the first match the rows of the second. If they do, you're allowed to proceed. And now the heavy lifting starts, how to actually multiply. Okay, breathe in, exhale, here we go. Explaining how to multiply a matrix is a little complicated, so instead of writing it down as a step-by-step process, let's work through one together. I think doing it is easier than explaining it, and then I'll let you try one on your own. So, question 6. What is the matrix product of 1364 and MPQW? So first, we have to make sure that the product is defined. So we do what we've been doing. List the rows and columns and the rows and columns. That first one has 2 rows, 2 columns, and so does the second. 2 by 2 and 2 by 2. The numbers in the middle match. We're allowed to multiply. Now, before we go any further, let's talk about what the final answer will look like and how to determine the final dimensions. The final dimensions will have the same number of rows from the first matrix and the same number of columns from the second matrix. Or just to give that a visual, we list rows by columns and rows by columns, but now it's the outer numbers that we're going to look at. The rows from the first and the columns from the second. So with the example before, we have 2 by 2 and 2 by 2. Look at those outer numbers. 2 rows, 2 columns. That means that the final answer will look something like this. 2 rows, 2 columns. That's what we're going for. Once you have the dimensions set up, you could now begin to multiply. The question is, how? The golden rule. In order to multiply, you must follow the rows of the first matrix and the columns of the second matrix. But what does that mean? Let's give it a shot. It's more helpful to show you than to just tell you. So again, we're starting with the first row of the first matrix and the first column of the second matrix. So let's give that a visual. We'd be starting with these two terms. Going by that first row in the first matrix, following the arrow would go to the 1. And in the second one, following the arrow to the column would give us the m. And you multiply those two terms. So that gives us 1m. And now we go simultaneously across that row and down that column. So from the 1, we would move to the 3, but simultaneously from the m, we'd move to the q. So not only do we multiply 1m, we also add to that product 3q. So that top left spot would be 1m plus 3q. And now we do the same thing in each corner. Again, the key is to move across the row at the same time that you move down the column, and then add the sum of those products. Let's do it rather than talk about it. So in the top right spot, what's going to go there? Well, if we're in the top right, that means we're still in the first row of the first matrix, but now we're in the second column of the second matrix. So, follow the arrows. We're going to go to the 1 and the p. That would be the first product, 1p. And what comes next? Now we follow that very technical process, so, or to put another way, remember, you go across and simultaneously you go down. So from the 1, we move across to the 3, and from the p, we move down to the w. So after the 1p comes 3w, and that would go in the top right. Now we do the same thing in the bottom left. If we're in the bottom left, it means for the first matrix, we're dealing now with the second row, and for the second matrix, we're still in the first column. So follow those arrows. Second row, first column. That would be the 6 and the m. And now we follow, so across and down. So from the 6, across to the 4, simultaneously with the m down to the q. So 6m plus 4q. So if you're starting to get the hang of it, I'll give you a minute to think about that bottom right spot. Think about the second row of the first matrix and the second column of the second matrix. Press pause, give it a shot. So that bottom right spot would be the second row and the second column. That means we're starting with the 6 and the P. And now we go across and down. So from the 6 across to the 4 and the P down to the W. So that spot would be 6P plus 4W. Now you might be saying, Daniel, what the hell was all of that? So let's do it again with another example. Practice makes perfect. Question 7. What is the matrix product of 5213 and CTEP? I'll help you start. Remember, we have to start by asking if it's defined. And in order to do that, we have to list the dimensions of each. So that first matrix has 2 rows and 2 columns, 2 by 2, and the second one, again, 2 rows and 2 columns, 2 by 2, 2 by 2. It's the same as the last example. We are allowed to multiply. And because it's the same as the last example, the dimensions will be the same as well. But now we go to those outer numbers. Rows of the first, columns of the second, 2 by 2. So the final answer will have 2 rows and 2 columns. It'll look something like this. So how do we start? We're in that first row and that first column. That means the 5 and the C. And following the arrows, from the 5 across to the 2, and from the C down to the E. So that top left spot would be 5C plus 2E. Same thing for the top right spot. What's going to go there? Now we're in that first row, but now the second column. So that would be 5 and T, and following those arrows, 5 across to the 2, and T down to the P. So the top right would be 5T plus 2P. And we're going to do the same thing with those 2 spots on the bottom. See if you could try. Press pause, give it a shot. So for that bottom left spot, we're in the second row and now the first column. So 1 and C, and then moving, so 1 across the 3 and C down to the E. So that would be 1C plus 3E. And now for the bottom right, second row, second column. So we'd be starting with the 1 and the T. The very technical operation, across and down, the 1 across to the 3 and the T down to the P. So that would give us on the bottom right 1T plus 3P. Now other matrix products can have different dimensions. However, the rules are always the same. As long as the columns of the first matrix match the rows of the second, you can multiply. So let's try one now with different dimensions. Question 8. What is the matrix product of CDEF and 157x30? So we always start by listing the dimensions. The first one is another 2 by 2, 2 rows, 2 columns. That second one has 2 rows, but now it has 3 columns. So we have 2 by 2 and 2 by 3. So it's defined. We can multiply. The numbers on the inside match. But the final dimensions will be a little different this time. Remember, for the final dimensions, we use those outer numbers. That first matrix has 2 rows, and that second matrix has 3 columns. So our final answer will have 2 rows and 3 columns. It'll look something like this. And now, how do we start? I'll help for the first spot. In that top left, that means we're in the first row and the first column. That would be C1, and then we do everyone's favorite operation. So across and down, C to the D, and 1 to the X. So the top left would be C1 plus DX. Now what will go in the next 2 spots? I'll let you work on it. Press pause and see if you could figure them out. So in that top middle spot, that means we're in the first row and the second column. So following those arrows would give us C5 and then to the D and the 3. C5 plus D3. And the top right, first row, third column. So now it would be the C times the 7 plus the D and the 0. And there's your whole top row. And if you're getting the hang of it now, I'll give you a shot to work on the bottom. Press pause and see if you could figure out all 3 spots. So looking at that bottom left spot, we're in the second row and the first column. So that would be E times 1, and then moving and moving would be F and X. E1 plus Fx. Now it's the bottom middle, second row, second column. That's going to be E5 and then F3, adding those products. And finally the bottom right, that's going to be the E times the 7, and then moving and moving to the F and the 0. And that whole thing is the final answer. So once you get the hang of it, it's not so bad. Just takes a little practice. And this can also come up on a word problem. Let's see how. A Broadway theater has 500 seats in the orchestra, 300 seats in the mezzanine, and 200 seats in the balcony. The ticket prices for those sections are, respectively, $179, $129, and $99. If the theater sells out every seat at full price, which of the following Matrix products represents the full amount of what the audience paid? Give it a try. Press pause, see if you could do it. So if you tried to work with the first two, A and B, you would have seen that you couldn't multiply them. The columns of the first did not match the rows of the second. Those products were undefined, so A and B are out. Now C, D, and E were all defined. You can multiply them. However, look carefully at the numbers in C. The numbers are in the wrong order. The ticket prices don't match with the type of seat, so we could also eliminate C. So that leaves us with D and E. Working with those, we would see that D works out perfectly. Let's see how. The prices in the first bit, $179, $129, and $99, match up perfectly with their counterparts of how many seats. Multiplying this matrix would give us 179 times 500 seats, plus 129 times 300 seats, plus 99 times 200 seats. And because we're adding across, that would give us the final amount. Now, choice E would also have the correct numbers match up between prices and types of seats. However, you wouldn't be adding them across, you would just be listing the numbers. That's why the answer is D and not E. And let's look at one more topic. If they want to be extra obnoxious, they might ask how to find the determinant of a matrix. This is not so bad if the question tells you how to find it, but sometimes they won't, so let's break it down. Question 10. What is the determinant of this matrix? 4, 3, -7, and 1. To find the determinant of the matrix is not so bad. It's just a very random topic that they sometimes define for you, but other times they don't. So just to look at this example for a moment, if you're given the matrix ABCD, the determinant is to crisscross the products and then subtract them. In other words, AD minus BC. So let's use that on the matrix above. With those numbers, that would be 4 times 1 minus 3 times -7. That works out to be 4 minus -21, or 4 plus 21, which is 25. The answer is 25. Remember what we said in video 6. The ACT is unfair. They sometimes will throw in topics that have never appeared on the test before, or on certain tests they will define a determinant and how you could find it, and on other tests they won't. But either way, now you're covered. You know how to find it. Crisscross the products and subtract. AD minus BC. I hope you found this video helpful. Again, these questions are definitely worth some points on the ACT, so follow the steps that we covered here. Always start by seeing if the dimensions allow you to multiply, and then from there follow that very technical procedure, across in one and down in the other. Keep practicing and you'll get the hang of it. I'll see you next time. And remember, plan your work, work your plan.